When the first major combat operations broke out in Europe, the primary mission for single-engine fighters on all sides of the conflict was destroying enemy aircraft. That meant going after everything, from heavy bombers to enemy fighters. To pull this off, an airplane had to be incredibly maneuverable. Pilots absolutely had to hold their own in a classic turning dogfight. This was when fighters squared off one-on-one. Besides maneuverability, designers chased top speed and rapid acceleration. They also needed an excellent rate of climb and the ability to dive on the enemy at high speeds. But as the war escalated, the rules of the game began to change. Before long, German single-engine fighters were expected to do more than just score aerial victories. They had to take on ground attack and even fighter-bomber roles. Designers had to make their aircraft significantly more versatile. But the biggest headache for engineers turned out to be a completely different challenge. They had to design a dedicated high-altitude interceptor. This meant solving a whole range of incredibly complex technical issues. By 1941, the British realized just how dangerous enemy high-altitude bombers and reconnaissance aircraft could be. For Britain, this threat was so serious that it became the main driving force behind developing specialized high-altitude fighters. These aircraft needed to be equipped with pressurized cockpits. Right around the same time, the United States also started developing similar aircraft. However, they did not treat the project with quite the same sense of urgency. Meanwhile, development was in full swing over in Germany. German engineers were actively experimenting with pressurized cockpits for fighters. They were developing turbochargers and looking for new ways to boost engine power at high altitudes. However, the Luftwaffe High Command did not see the high-altitude threat as being nearly as critical as the British did. German generals were still dismissing the need for defensive tactics. They were pinning all their hopes on an ambitious program known as Bomber B. The goal there was to create an advanced high-altitude bomber that would be practically untouchable by enemy interceptors. But even with the bulk of resources pouring into bomber development, the Reich Air Ministry Technical Office stood firm. They insisted that developing specialized high-altitude fighters would still be crucial for the future of the war. Curiously, the push to increase the service ceiling for German fighters started long before the legendary American B-17 bombers ever showed up in the skies over Germany. These heavy bombers could comfortably cruise to their targets at altitudes that most fighters of the day simply could not reach. When the United States officially entered the Second World War, the Luftwaffe and Reich Air Ministry leadership were holding on to some serious false hopes. They genuinely believed the Americans would be tied down in the Pacific theater. They thought the United States simply would not have the resources to commit major air assets to the European theater of operations. As early as late 1940, the Focke-Wulf Company began working on an ambitious new project. They decided to develop an aircraft based on their legendary FW-190 fighter. This new airplane was meant to operate at much higher altitudes than the base model FW-190 that had just been ordered into production. The engineers planned to use the powerful BMW 801 engine. To improve its high-altitude performance, they wanted to use a specialized nitrous oxide injection system. Alternatively, they considered fitting it with the latest turbochargers from the German Aviation Research Institute and the Hertz Company. At the same time, industrial giants Daimler-Benz and Junkers were not sitting idle. They were actively testing their powerful new DB603 and Jumo 213 engines. It did not take long for ideas to emerge on how to integrate these advanced power plants into the FW-190 fighter. After weighing all the options, the Reich Air Ministry allocated 15 FW-190 airframes for testing. Engineers used these test beds to continuously evaluate new engines, boost systems, turbochargers, and pressurized cockpits while measuring high-altitude flight performance. Eventually, these bold experiments evolved into three main development paths. The first was a high-altitude fighter with a pressurized cockpit. It was designated the FW-190B. Since a reliable turbocharger was not ready yet, they fitted this variant with the proven BMW 801 engine. This was paired with a GM-1 boost system. The second path was another high-altitude fighter with a pressurized cockpit, the FW-190C. This aircraft utilized the powerful DB603 engine. It could be run either with a two-stage supercharger and nitrous oxide injection, or with a brand new exhaust-driven turbocharger. Finally, the third option was a medium-altitude fighter, the FW-190D. They decided not to overcomplicate this airframe with a pressurized cockpit. They opted instead to equip it with the reliable Jumo 213 engine. To test all these concepts in practice, engineers plan to build 6 prototypes for each of the 3 variants. Flight tests of the first experimental FW-190B series aircraft were frankly underwhelming, and they deeply disappointed the engineering team. Right at the start of the testing phase, they decided to drop the GM1 boost system and the stock BMW-801 engine. They replaced them with the newer DB603. Because of these changes, the fighter effectively became a testbed for the upcoming C-Series, even without a pressurized cockpit. The second B-Series prototype was built to the exact same specifications. In April 1942, both of these aircraft, now equipped with powerful DB603 engines, underwent rigorous high-altitude trials in Bremen. Later on, the second prototype received an even newer engine modification. It was then tested at Echterdingen. They decided to retain the older BMW 801 engines on the remaining 4 B-Series prototypes. However, they finally fitted them with pressurized cockpits. This was the entire purpose of the B-Series to begin with. However, it soon became clear that the C-Series fighters offered much greater combat potential. This made any further testing of the BMW 801 equipped aircraft a dead end. The first C-Series prototype began its trials with a pre-production DB603 engine. It featured a custom turbocharger, a 4-bladed propeller, and a fully pressurized cockpit for high-altitude flight. 2 more of the 5 aircraft in this series were fitted with turbochargers from Herth Motoren. In practice, however, the engineers ran into constant technical issues. The units from both manufacturers proved to be so temperamental that designers had to abandon them. They went back to a more reliable, proven setup. This was a 2-stage supercharger paired with a nitrous oxide injection system to boost power. Turbochargers were simply too immature of a technology at the time. They required significant refinement, especially to ensure reliability under harsh combat conditions. By the fall of 1942, despite all the optimistic estimates of the German High Command, one uncomfortable truth had become clear. The United States Army Air Forces planned to concentrate a massive armada of heavy bombers in the British Isles. Their main goal was to deliver devastating strikes directly at the heart of the Third Reich. The situation was escalating fast. American B-17 bombers were already causing major headaches for German interceptor squadrons. At the same time, new intelligence was downright alarming. It indicated that the Americans were gearing up to mass produce an even more formidable giant. This was the B-29 bomber. This aircraft featured a pressurized cabin. It flew much faster and could reach previously unattainable altitudes. Facing this threat, Germany desperately needed to develop its own next-generation high-altitude fighter. Leading aviation manufacturers Focke-Wulf and Messerschmitt were ordered to urgently submit concepts. The goal was to design what was essentially a superfighter. The new aircraft needed to have an exceptionally high service ceiling. It also required the ability to fly, demanding high-altitude reconnaissance missions. The massive government development program was split into 2 key phases. The first phase was labeled urgent. It required creating a fighter based on existing airframes. This approach relied heavily on off-the-shelf components from previous models to save precious time. The second phase was labeled deferred. It called for designing a completely new, purpose-built, high-altitude fighter and reconnaissance aircraft from scratch. During the urgent phase, Focke-Wulf proposed 2 variants based on their proven FW-190. They planned to pair the existing airframe with the powerful Jumo 213 engine. Meanwhile, their competitors at Messerschmitt bet on their legendary Bf-109. They pitched a variant with a significantly extended wingspan. For the deferred phase of the program, Focke-Wulf presented a major overhaul of the FW-190. This featured significant structural changes and vastly improved aerodynamics. Messerschmitt, in turn, proposed the advanced Me-155 concept. The technical department carefully reviewed all the proposals and ultimately approved them. However, in August 1943, all work on the Me-155 project was abruptly transferred. It was handed over to another well-known manufacturer, Blohm and Voss. Looking at the initial urgent proposals from Focke-Wulf, the baseline variant retained the standard wing of earlier FW-190 models. The second variant, however, featured a significantly extended wingspan. This was optimized for maneuverability at extreme altitudes. Wingspan aside, the two aircraft were practically identical. Both were powered by the Jumo 213 engine. Engineers fitted this engine with an advanced two-stage supercharger and an intercooler. This setup allowed the fighter to reach much higher altitudes than its predecessors could with their baseline engines. Both prototypes featured pressurized cockpits to protect the pilots. They could also be equipped with the specialized GM-1 and MW-50 boost systems. These systems provided a sudden surge of power during combat. Engineers also decided to swap out the electrical systems for the flaps and landing gear. They replaced them with more reliable hydraulics. To accommodate all this new equipment, the fuselages of both aircraft had to be noticeably lengthened. To maintain the center of gravity, the cockpit was moved aft by about 15.7 inches. The tail section was also enlarged to improve flight stability. As for armament, these high-altitude interceptors packed a serious punch. They featured a powerful 30mm cannon firing directly through the propeller hub. They also had two 20mm cannons in the wing roots and two additional 20mm cannons mounted in the fuselage. By that time, the influence of the company's chief designer Kurt Tank had grown significantly. New aircraft were being designated with the letters TA in his honor right from the drawing board. This replaced the familiar FW. However, the new high-altitude variants were fundamentally different from their predecessors. A name change was practically inevitable, a perfectly logical step in the continued development of the series. As a result, even before the end of 1942, these new aircraft received the official designation TA-152. Both versions were developed as a direct continuation of the famous FW-190 fighter. Because of this, the German Air Ministry decided not to break tradition. They kept the predecessor's familiar letter designation system. At that point, the aircraft powered by BMW 801 engines had just entered full-scale production. They received the designations FW-190F and FW-190G. Following bureaucratic logic, the next new models should have been named TA-152H and TA-152K. However, chief designer Kurt Tank had a different vision for the project. He planned to create a standard span version for fast bomber escort. He also wanted a long span version to serve as a dedicated high-altitude fighter. Tank's influence in official circles was very strong. The ministry eventually went along with him. These two variants were designated TA-152B and TA-152H. The letter B had already been used for an earlier high-altitude version of the FW-190, powered by a BMW 801 engine. But since that older project never really panned out, officials had no problem reassigning it to Tank's new fighters. One of the first experimental projects involved installing a powerful DB603 engine from Daimler-Benz. This was fitted into the basic airframe of the FW-190D. This engine was intended to be fitted with a turbocharger. It could even be developed into a completely new and significantly upgraded variant. The aircraft's design itself underwent major changes. This was especially true when it came to the wings. Engineers completely redesigned the structural framework. The front spar was shortened to the landing gear attachment point. Meanwhile, the rear spar was extended across the entire wingspan. To make sure the structure did not lose its strength, additional ribs were used. They were spaced much closer together inside the wing. Kurt Tank pushed the Air Ministry as hard as he could. He demanded that the new TA-152 be put into full-scale production immediately. However, leadership pushed back hard. The new airplane was simply too different from the familiar FW-190. Nobody wanted to disrupt a well-established assembly line. They refused to retool right in the middle of the war. So at first, officials demanded a simpler approach. They wanted to upgrade the aircraft already on the production line. Because of that bureaucratic resistance, the TA-152 development program stalled. This delay lasted until the spring of 1944. Only then did the first real opportunity arise. They could finally tool up for this fighter at a major aviation plant in the city of Sorau. Meanwhile, engineers took one of the old FW-190C prototypes. They completely rebuilt the aircraft. Their main goal was to test out new technical solutions. This primarily involved the updated wing planform. This new wing had a slightly larger span and area compared to the FW-190D model. It not only improved the aircraft's aerodynamics, the wing was also much easier to manufacture. Most importantly, it allowed them to fit an extra fuel tank right in the center section. At the time, the Luftwaffe was in desperate need of a new fighter. They needed a plane that could go toe-to-toe with the American Mustangs. Because of that, the technical department made a fast decision. They immediately proposed installing this optimized wing on the new TA-152. Against this backdrop, new debates arose. Kurt Tank held out until the very end for the DB603 engine. Meanwhile, the technical department flat out demanded the Jumo 213. Management did turn a blind eye to the fact that Tank was unofficially continuing experiments with his preferred engine. They even let him roll out a TA-152C test prototype powered by the DB603. This made sense. Parallel work on the FW-190C had been completely shut down due to constant turbocharger issues. Another interesting development was the TA-152E reconnaissance aircraft. This was based on the TA-152B airframe. It inherited its E designation from an earlier recon project based on early FW-190 variants. Meanwhile, over at the assembly plant in Sorau, they had already started putting together the first examples of the TA-152H series. These airframes were slated to be flying testbeds for components meant for other variants. Because of this, a parallel production line had to be prepped in Cottbus to avoid slowing down overall production. The initial batch of these aircraft received the Versuch designation. This is German for experimental or prototype. The baseline for the entire series came from the first 5 aircraft built. 2 prototypes were completed in June and July of 1944. They were initially sent to Langenhagen for flight testing. By August, 1 was transferred to the Rechlin test facility for rigorous official trials. By this point, engineers had started converting 5 older FW-190C prototypes to the new TA-152 standard. The first of these modified fighters took to the skies on July 12, 1944. This happened right before the purpose-built prototypes made their appearance. The first TA-152H test aircraft already featured the new long-span wing, though without the extra fuel tanks installed yet. Those would only be fitted on subsequent production models. One of the rebuilt prototypes was used strictly for structural testing of this new wing. To save as much weight as possible, the airframe was completely stripped of its armament. The DB603 engine was swapped out for a powerful Jumo 213E1 with a new engine mount. Also, a massive 3-blade VS-111 propeller was fitted up front. To properly balance the modified aircraft, the wing mounting points had to be shifted forward by exactly 400 millimeters, about 15.5 inches. This exact configuration was ultimately carried over to the final production version of the TA-152. The fighter's new wing had a span of over 47 feet. It featured an impressive and well-engineered design. Just aft of the front spar in each wing, engineers managed to fit 3 fuel tanks. The inner tank in the left wing held about 18.5 gallons of a water-methanol mixture for the MW50 boost system. This technology significantly boosted the powerful Jumo 213E1 engine. It increased its output from 1,750 to 2,050 horsepower during takeoff. It also maintained 1,800 horsepower at an impressive altitude of 26,000 feet. On top of that, at altitude, the ejector exhaust stacks produced nearly 485 pounds of residual thrust. This added to the aircraft's top speed. The remaining wing tanks had a combined capacity of around 105 gallons. They were filled with standard 87 to 89 octane aviation fuel. A larger 156-gallon main fuel tank was housed in the fuselage, directly beneath the cockpit. Just aft of that, the designers included a 22.5-gallon cylinder of nitrous oxide for the GM1 system. This was injected into the supercharger at high altitudes. It allowed the engine to produce 1,740 horsepower, even in the thin air at nearly 32,000 feet. However, unfortunately for the team behind the cutting-edge TA-152 program, one of the primary FW-190 test prototypes crashed. It was completely destroyed on only its second flight, which took place on July 13, 1944. The next FW-190 prototype, which also served as a flying testbed for the TA-152 program, took to the air for the first time on August 6, 1944. Unlike its predecessor, it featured a standard engine mount and lacked the extra wing tanks. However, this aircraft met a similarly grim fate. It was destroyed in a crash after only a week of intense flight testing. A third experimental prototype was completed by the end of September that same year. It rolled out right alongside 3 pre-production TA-152 test planes. Their cockpits were pressurized, built as sealed pressure capsules. This protective capsule was enclosed by armored front and rear bulkheads, reinforced side panels, and a heavy-duty floor. The canopy featured a thick, armored glass windscreen. Its sliding section was hermetically sealed with rubber gaskets. Thanks to this design, the pressure differential inside the cockpit was maintained at around 4.3 pounds per square inch. This allowed the pilot to operate comfortably without an oxygen mask at high altitudes. Its armament was truly formidable. It included a heavy 30mm Mk-103 cannon firing directly through the propeller hub with 80 rounds. It also had 2 wing-mounted 20mm MG-151 cannons, each with 175 rounds. 2 more FW-190 test aircraft joined the flight program in October and November 1944. They were fitted with different wing designs adapted from later variants of the fighter. The first was powered by a Jumo 213E1 engine and stripped of all armament. It crashed just 2 days into its flight testing. Meanwhile, the second prototype was already being modified for a follow-on fighter project. Initially, it was fitted with a Jumo 213F engine and flew unarmed. But 3 weeks later, engineers reversed course. The aircraft was re-equipped with the proven Jumo 213E1 engine and a full combat loadout. This included the wing-mounted MG-151 cannons and the state-of-the-art MG-213 centerline cannon from Mauser. This unique revolver cannon featured interchangeable barrels and chambers. This allowed it to fire either 20mm or 30mm ammunition, depending on the mission profile. By the end of the year, the German aviation industry ambitiously planned to produce 4,000 of these versatile cannons per month. The specific aircraft intended to serve as the very first fully-fledged experimental prototype for the new TA-152 series did not actually take to the air until March 1945. That was a full 4 months after the Cottbus plant had already started delivering production airframes. The very first TA-152 fighters to roll off that assembly line belonged to a batch of 20 pre-production aircraft. In October and November 1944, they were immediately delivered to a special test detachment formed at the Rechlin test facility. This unit was commanded by the experienced test pilot Bruno Stolle. Even though the primary role of the team was supposed to be familiarizing themselves with and testing the new hardware, the harsh realities of the war forced them into frontline service as an operational combat unit. Later, starting in November 1944, the pre-production models on the Cottbus assembly line were replaced by fully operational combat variants of the TA-152. These began entering full-scale production. In total, by the end of that same year, German industry managed to produce 34 of these fighters. The pre-production fighters differed from the final combat versions in only one major way. They lacked the internal fuel tanks in the wings. The heart of these fighters remained the powerful Jumo 213E1 engine. Firepower was provided by a hub-firing Mk-108 cannon with 90 rounds. This was along with 2 MG-151 cannons mounted in the wing roots with 175 rounds each. To protect the pilot and critical engine components in combat, the aircraft was fitted with about 330 pounds of steel armor plating. The radio equipment consisted of the standard FUG-16ZY and FUG-25A communication systems. But for special missions, the aircraft were fitted with the advanced FUG-125 Hermine navigation and landing system. This was usually integrated with a newly developed Siemens autopilot. To maintain visibility in rain, snow, or fog, the canopy featured a special heated windshield. One of the first TA-152 fighters built in Cottbus was the first to receive this all-weather equipment package. Engineers plan to incorporate this setup into the majority of future production aircraft. As mentioned before, the main fuel tanks inside the fuselage held 156 gallons. But for long-range flights, you could easily attach a standard 300-liter drop tank right under the belly of the aircraft. On the special all-weather version of the fighter, engineers decided to omit the GM1 nitrous oxide system. In its place went a tank for the MW50 water-methanol mixture. This provided a significant power boost and a real speed advantage during low and medium altitude dogfights. Thanks to this impressive performance and the extended range, Luftwaffe High Command was not just looking at these new aircraft as standard interceptors anymore. They saw them as true long-range escort fighters. Let's look at the basic weight specifications. The empty weight of the TA-152H0 fighter was right around 8,490 pounds. Normal takeoff weight without the wing tanks was around 10,430 pounds. Meanwhile, the TA-152H1 version, fully loaded with wing tanks, weighed over 11,500 pounds. Most production aircraft were equipped with a special 70-liter wing tank for the MW50 boost system. They also had a cylinder for the GM1 nitrous oxide system located just behind the cockpit. Even though the wing tank significantly extended the flight range, military leadership still did not think it was enough. That is why in April 1945, these fighters were fitted with an additional 280-liter fuselage tank behind the cockpit. To make sure the aircraft did not shift its center of gravity too far aft from that extra weight, the GM1 cylinder had to be moved closer to the engine. They even installed a 22-pound counterweight. German engineers were also pushing forward with the TA-152H2 variant. It featured significantly upgraded radio equipment. However, by mid-December 1944, development on this series was completely shut down. The designers even explored equipping it with massive 24-cylinder Jumo 222E or Jumo 222F engines featuring complex supercharger systems. Those ambitious plans stayed on paper, though, as work on the engines themselves was eventually scrapped. Up until March 1945, they were also developing a heavily armored version powered by a DB603E engine. Due to severe material shortages late in the war, these aircraft were actually rolling off the assembly line with wooden tail sections. There was one more unique version. This was the high-speed TA-152H10 reconnaissance variant. The military planned to build 20 of these aircraft per month starting in May 1945. Instead of extra armament, a heavy-duty aerial camera was mounted behind the cockpit. This recon plane was incredibly impressive. Cruising at almost 32,000 feet at 373 miles per hour, it had a range of 745 miles. Its top speed reached an unbelievable 429 miles per hour at over 34,000 feet. All of this with a takeoff weight of almost 11,660 pounds. In total, only 150 TA-152H1 fighters rolled off the assembly line at the Cottbus plant. Production had to be urgently shut down due to the rapid advance of the Red Army. Today, historians have no evidence that a single Luftwaffe unit was fully equipped with these state-of-the-art aircraft. A few squadrons operated them mixed with the well-known FW-190D series and other aircraft. They primarily flew dangerous ground attack missions. Some units used these fighters to fly top cover for the takeoffs and landings of Me-262 jets. In practice, most of the TA-152 fighters produced were destroyed on the ground before the Luftwaffe ever had a chance to officially adopt them. On top of that, the Germans used a very small number of these aircraft in their Mistel composite aircraft program. Now let's look under the skin and dig into the engineering. If you compare the fuselage of the TA-152H with its predecessor, the FW-190A8, you can spot a few key design changes. First, the designers had to stretch the nose of the aircraft by about 30 inches. This was necessary to accommodate the massive hub-firing Mk108 motor cannon. It also made room for two MG151 cannons. If needed, the primary weapon could easily be swapped out for an Mk103. The designers wanted to simplify the factory assembly process. Because of this, the new extended section was attached to the main fuselage using standard high-strength bolts. Here is another important detail. The wing of the aircraft had to be moved forward by 16.5 inches. This was a critical step to maintain the center of gravity. As a result, engineers had to completely redesign the internal mounts. They also had to relocate part of the structural frame. To create room for the forward fuel tank, they redesigned the outer skin and access panels. The designers needed to ensure the aircraft handled smoothly. It also had to maintain stability during aggressive maneuvering. To achieve this, the tail section was lengthened by adding a 20-inch plug. This extra space provided a convenient spot to house the oxygen and compressed air bottles. A longer fuselage, of course, meant higher bending moments during flight. The structure was significantly reinforced to help the airframe withstand these extreme loads. Earlier models used lightweight duralumin parts. Here, the engineers opted for high-strength steel extrusions instead. Finally, let's talk about pilot comfort and survivability. A pressurized cockpit was located in the center of the fuselage, right above the fuel tanks. It had a volume of around 35 cubic feet. All joints and rivets were carefully sealed with a specialized paste. This prevented air from leaking out at high altitudes. The edges of the canopy were cleverly sealed using a tubular rubber gasket. This gasket ran the entire perimeter. Inside, it was partially filled with porous rubber. It was also pressurized with air to around 37 pounds per square inch. This air was constantly supplied by a small, 1-liter compressed air bottle. If the pilot had to bail out during combat, the canopy jettison system was highly reliable. The sealing hose vented instantly, the locking mechanism released automatically, and an explosive cartridge blew the canopy clear, opening an escape path for the pilot. To provide better protection during combat, the canopy featured double-glazed armored glass. The outer layer was 8 millimeters thick. The inner layer was 3 millimeters. Engineers wanted to prevent fogging and keep the air gap bone dry. To do this, they fitted 8 silica gel capsules around the edges to absorb any moisture. Inside the cockpit, all the vital fluid lines and hoses were reinforced. This allowed them to safely handle high flight pressures. Access to the radio was provided by a small hatch. This hatch was equipped with a quick release latch and heavy-duty rubber seals. These seals prevented any loss of cabin pressure. The maintenance panels for the twin MG-151 cannons on the C and H variants of the TA-152 featured a similar airtight design. All these carefully engineered details ensured the fuselage was fully sealed. This was absolutely critical for keeping the pilot alive at extreme altitudes. The main landing gear and its struts were carried straight over from the standard FW-190A8. However, there was one major upgrade. The old electrical retraction system was replaced with a much more reliable hydraulic drive. The massive main wheels measured 740 by 210 millimeters. This ensured the aircraft stayed firmly planted and stable during takeoffs and landings. The tail section, specifically the horizontal stabilizers and elevators, was another direct carryover from the FW-190A8. However, designers wanted to give the aircraft better stability and more predictable handling. To achieve this, they significantly increased the surface area of the vertical fin. Out back, the tail wheel measured 380 by 150 millimeters. The tail surfaces were designed as a single modular unit. This unit was joined to a 50-centimeter fuselage plug. Because of late war material shortages, these components could easily be built out of wood. When they went that route, the extra intermediate plug was not even needed. This was because the lengthened wooden tail section mounted directly to the rear fuselage as a single solid piece. Since the new fighter featured a much wider wingspan, the ailerons and flaps had to be lengthened to match. And just like the landing gear, the old electrically driven flaps were upgraded. They were replaced with a modern, heavy-duty hydraulic system. The longer fuselage brought about another change. The standard control linkages had to be significantly extended. Wherever these control cables passed through the pressure bulkhead, they were fitted with airtight seals. This was done to maintain cabin pressure. On top of that, the internal structure of the wings was heavily reworked. This was necessary to make room for additional internal fuel tanks. Dropping in the new engine extended it much further past the nose. This forced the designers to push the main landing gear outward by 250 millimeters, closer to the wingtips. To make that happen, they had to extend the inner spars by 0.5 meter. The entire wing root also had to be redesigned from scratch. You would see the same modification on both the TA-152C and H variants. That massive wingspan stretched out to over 47 feet. This meant they needed much thicker skin on the inner wing sections. Even though the maximum allowable G limits of the aircraft dropped slightly, the fundamental wing design stayed true to the legendary FW-190. The heavy forward spar took the brunt of the bending loads. It transferred that stress back to the rear spar. That rear spar did not just maintain the shape of the wing, it was also beefed up with extra stiffening webs. And to make life easier for the mechanics working on the retracted gear, engineers added some really convenient quick-release access panels. Stuffing 3 flexible fuel cells into the wings meant reinforcing the internal framing. This was especially true for the ribs and stringers. To actually install those cells, they cut circular access panels into the underside of the wings. These panels measured 200 millimeters across, and to make field repairs on damaged aircraft as painless as possible, the outer wing panels were made completely detachable halfway down the span. This joint was locked tight using wedge-shaped splice plates. Heavy-duty bolts clamped down on the spar caps to secure it. The beating heart of this interceptor was the liquid-cooled inverted V12 Jumo 213E. It came equipped with an advanced 2-stage supercharger. This let the fighter lay down incredible power figures across a wide range of altitudes. All this power was translated into thrust by a wooden 3-blade Junkers S9 variable pitch propeller. It measured 3.6 meters, about 11 feet 10 inches in diameter. The plan was to eventually swap it out for a more advanced 4-blade VS19 measuring 3.5 meters across. Even though it was slightly smaller, the 4-blade design would have been much more efficient. It would translate the engine's massive horsepower into high-altitude performance far more effectively. As an alternative to the standard Jumo 213E, engineers left enough room in the cowl to install the high-altitude DB603LA or L series engines. Mounting these power plants required only minor tweaks to the airframe itself. They also had to adjust the engine control linkages, the cabin pressurization blower, and the propeller pitch mechanism. To boost power at low and medium altitudes, the designers integrated the MW50 system. Here is how it worked. A 70-liter tank filled with a water-methanol mixture was housed inside the inner left wing. When the pilot engaged the system, it allowed the engine to run at much higher manifold pressures. Aside from a massive jump in horsepower, the mixture acted as an anti-detonant fluid. It drastically lowered the intake charge temperature and cooled the cylinders from the inside to prevent engine knock. At a consumption rate of roughly 150 liters per hour, that 70-liter supply was enough for about 28 minutes of continuous operation in boosted mode. If a dogfight shifted to high altitudes, another piece of technology came into play. This was the GM1 system. Engaging this provided a massive power boost, adding an impressive 410 horsepower. To make it work, an 85-liter tank of liquid nitrous oxide was installed in the rear fuselage. The pilot could manually control the flow rate. They could switch between 60, 100, or 150 grams per second. At the medium flow rate of 100 grams per second, a full tank provided enough nitrous oxide for 17 minutes of peak performance at extreme altitudes. As for the fuel system, the forward 233-liter fuselage tank was carried over from earlier production variants without a single change. However, since the designers had to shift the Interceptor's wing forward slightly, this tank was moved along with it. This turned out to be a brilliant move. It freed up space and allowed them to increase the rear tank's capacity to 362 liters. Thanks to this, the total internal fuel supply in the fuselage jumped to 595 liters. That fuel had to be reliably protected from enemy fire. 16mm armor plates shielded the tanks from the bottom and sides. Meanwhile, sturdy 12mm plates covered them from above. The engineers fully understood that this interceptor needed maximum range, so they incorporated a few interesting solutions. For example, a standard 300-liter drop tank could be slung under the fuselage of the TA-152H0 variant. It was highly streamlined, minimizing aerodynamic drag. Once it ran dry, the pilot could simply jettison it. Fuel was transferred from this drop tank to the engine using compressed air to pressurize the tank. With the next version, the TA-152H1, the developers went even further. They housed 6 flexible fuel bladders inside the wings. This offered a combined capacity of 470 liters. One of these tanks in the left wing, holding 70 liters, was dedicated to the water-methanol mixture for the MW50 boost system. All of these fluids were also fed to the engine using compressed air. To service these flexible bladders, circular access panels measuring about 200 millimeters in diameter were added to the underside of the wings. If a mission called for extreme range, the standard 300-liter drop tank could be swapped out for a massive 600-liter external tank. The oil system also deserves a special mention. A 72-liter oil tank was positioned right next to the engine-mounted cannon, forward and to the right in the nose section. Surprisingly, this tank was completely unarmored. The designer's logic was simple. The massive engine sitting right next to it acted as a perfect shield against incoming fire all on its own. Typically, ground crews would fill it with 60 liters of oil. That was plenty for long-range sorties, with the internal tanks topped off at 595 liters, along with a 300-liter drop tank under the belly. The system also accounted for cold weather operations, allowing ground crews to dilute the oil with up to 25% aviation fuel to make the engine easier to start. With a heavy fuel load on board, the amount of fuel mixed into the oil would be reduced accordingly. As for the rest of the equipment, they pulled most of the assemblies and components directly from the FW190A8 production lines. This significantly streamlined the manufacturing process. Only the hydraulic mechanisms for the landing gear and flaps had to be modified slightly to work smoothly with the new Jumo 213E engine. And as mentioned earlier, to keep the pilot alive and capable at extreme altitudes, the aircraft was fitted with a dedicated cockpit pressurization and oxygen system. But we will cover that in detail a bit later. Imagine flying at extreme altitudes where the air is too thin to breathe. To ensure pilot survival, the cockpit was fully pressurized, and breathable air was supplied using a specialized Knorr compressor. This piece of equipment was incredibly reliable. It drew in fresh air before it even reached the cooling system, ran it through heavy-duty filters and valves, and only then fed it directly into the cockpit. In the event of a compressor failure, a fail-safe mechanism completely sealed the cockpit, locking the existing pressure inside and potentially saving the pilot's life. The real engineering magic kicked in when the fighter crossed the 26,000-foot mark. At that specific altitude, the compressor would automatically engage. From then on, it maintained a steady cockpit pressure of 5.3 psi. If the pressure suddenly dropped to 3.4 psi, a regulating valve would instantly kick in. This was absolutely critical to protect the pilot from the devastating effects of rapid decompression. When the aircraft was operating below 26,000 feet, the system functioned much more simply. Ram air flowed directly into the cockpit, completely bypassing the compressor. Thanks to a clever system of vents and valves, the pilot could manually dial in not just the internal pressure and fresh airflow, but also the cabin temperature. This meant that even in freezing skies, the cockpit was kept comfortably warm. If things got too hot inside during an intense high-altitude flight, a powerful cooling system took over. It used cold air drawn from the engine's 2-stage supercharger system, quickly bringing the temperature back down to normal. To ensure the pilot always stayed in contact with flight control, the aircraft was equipped with advanced radios for its time. But the instrument panel was packed with other impressive avionics too. It featured an IFF system, directional radio navigation instruments, a remote reading compass, a combined artificial horizon, and a special heading indicator to keep the pilot spatially aware. Now let's take a look at the firepower. Fighter variants like the TA-152H0 and TA-152H1 packed a serious punch. Mounted just forward of the cockpit, near the wing roots, were two 20mm MG-151 autocannons. Each gun carried 150 rounds and was hooked up to an electrical synchronization gear. This brilliant setup allowed them to fire safely right through the propeller arc without striking the spinning blades. But the true heavy hitter in a dogfight was the massive 30mm Mk108 autocannon. It was mounted directly inside the V of the engine block to fire through the propeller hub. It carried a 90-round magazine. Its barrel was angled slightly upward by exactly 35 arc minutes to compensate for the steep ballistic drop of the heavy 30mm shells. On top of that, underwing racks could easily be mounted to carry various unguided rockets. Keep in mind, the TA-152H was designed purely as a high-altitude interceptor and escort fighter. That is exactly why the designers did not even make provisions for bomb racks. Instead, for long-range missions, a 79-gallon drop tank could be attached under the fuselage. It could simply be jettisoned mid-air once empty. With enemy aircraft carrying increasingly heavy defensive armament, engineers had to heavily reinforce the cockpit armor. This gave the pilot a much better chance of surviving brutal high-altitude combat. The wing structure for the TA-152 series was designed with a massive safety margin. Based on a flight weight of 4,500 kilograms or 9,920 pounds, it easily handled high G loads. Many key components like the fuselage, or Rumpf in German, along with the tail section, were lifted directly from the related TA-152C model. These structures were so overbuilt that they far exceeded the requirements for standard fighters of the era. The heavy-duty engine mounts, meanwhile, were sourced from the TA-152E reconnaissance variant. This kept the power plant rock solid even under the extreme stresses of air combat.